Hello students, welcome to EPG Pathshala. I am Professor P.N. Kotru from Jammu. Today we are going to discuss about a module entitled Miller Indices and some crystallographic formulae under paper Crystallography and Crystal Growth. So students, let us see what we are going to learn in this module. We are going to have concept of Miller indices of crystal phases, Miller indices for hexagonal system, indices of crystallographic direction, and important crystallographic formulae, Miller indices of a crystal phase. The orientation of any phase or plane of a crystal is labeled by a set of three numbers called Miller indices. We first define a plane by taking the intercepts that it cuts on the three axes. Let us choose a lattice point O as origin and take OX, OY and OZ as positive directions along the three edges of the unit cell. We give the intercepts in terms of the dimensions of the unit cell, which are the unit distances along the three edges. That is, in terms of the primitive translations along the three axes. The procedure of determining Miller indices may be described as follows. This will be all explained sequentially. Take any atom of the crystal as the origin and choose coordinate axes from the atom in the direction of the basis vectors. Next, find the intercepts of the plane under consideration belonging to the system. Express these intercepts as integral multiples of the basis vectors along the three crystallographic axes. Then take the reciprocal of these numbers. Clear off the fractions by multiplying each by the least common multiple of the denominators. This will reduce it to three smallest integers having the same ratio. Suppose these integers are, say for example, HKL. The quantities within brackets HKL are then the Miller indices of that system of planes. Let us illustrate the method by taking the example of a plane whose intercepts are at the lattice distance small a, twice the lattice distance small b, that is twice b, and three times the lattice distance small c, that is 3 times c, as is shown in figure 6.1. Now take the reciprocals of these intercepts, which in this particular example are 1 by 1, 1 by 2 and 1 by 3. Multiplying each of the reciprocals by the least common multiple of the denominator 1, 2 and 3, which comes out to be 6. The numbers that we get are 6, 3 and 2. Place these three numbers in parentheses as 6, 3, 2. These are the Miller indices of the plane. The plane, we may say, is a member of the 632 family of planes. Let us consider some more examples and further explain the procedure of assigning Miller indices to crystal faces or planes. Suppose a plane cuts the x-axis at unit distance but is parallel to the y and z axis. So the plane cuts intercepts 1a, infinity and infinity along x, y and z axes respectively. Taking the reciprocals of these numbers, which are 1a, 0 and 0, the Miller indices of this plane therefore are 1, 0, 0 within brackets. This may also be called as YZ plane or BC plane. Similarly, indices of the planes that are parallel to x and z axes, that is AC plane, and of x and y axes, that is AB plane, are therefore within brackets 0, 1, 0 and within brackets 0, 0, 1 respectively. Taking unit cells of a simple cubic crystal, planes within brackets 1, 0, 0, within bracket 0, 1, 0, within bracket 0, 0, 1 and within brackets 1, 1, 1 are shown as shaded planes in schematic diagrams of figure 6.2a, b, c, d. Figure 6.2, it shows 1, 0, 0, 0, 1, 0, 0, 0, 1 and 1, 1, 1 planes of a simple cubic crystal. 1, 0, 0 plane is shown in figure 1a, 0, 1, 0 is shown in figure b, 0, 0, 1 is shown in figure c, and 1, 1, 1 plane is shown in figure d. 6 faces of a cubic crystal are assigned the indices as 1, 0, 0, 1 bar 0, 0, 0, 1, 0, 0, 1 bar 0, 0, 0, 1 and 0, 0, 1 bar as shown in the schematic diagrams. Within curly brackets 1, 0, 0 denotes the 6 faces of the cubic form. Figure 6.3, as is shown here in this slide, show faces of a cubic crystal with mirror indices 0, 0, 1, 0, 1, 0, 0, 0, 1 bar, 1, 0, 0 and 0, 1 bar 0. The curly brackets 1, 0, 0 denote the 6 faces of the cubic form. In crystallography, it is conventional to write the minus signs above and not before the Miller indices. The digits of 6 faces of a cubic crystal are 1 or 1 bar and 2 zeros. Likewise, there may be number of systems of planes whose Miller indices differ by permutation of numbers or of minus sign, yet they are all crystallographically equivalent planes in respect of density of atoms and interplanar spacing. In a cubic lattice, all the planes identified by permutations of 3 Miller indices among themselves, as for example, within brackets HKL, KHL, LHK, and so on, as well as those obtained by taking various combinations of minus sign, are all crystallographically equivalent. In the language of crystallography, we say the 6 faces of a cubic crystal belong to the same form. To show the crystallographic equivalence of the 6 faces belonging to the same form, of which within brackets HKL is a member, it is customary to enclose the Miller indices in curly brackets, that is curly bracket of HKL. In the case of the 6 faces of the cube form described here, the form is represented by curly bracket 100. For any crystal structure, a set of axes can be found for which the Miller indices reduce to simple integers or 0. This is known as law of rational indices. Miller indices of a hexagonal crystal are satisfied by choosing 4 axial directions: A1, A2, A3 and C. In this system, a plane is specified by 4 numbers as is shown in figure 6.4, which shows the Miller indices for a hexagonal system. We have talked about labeling of crystal planes. Now we shall talk about indices of crystallographic direction. Considering 3-dimensional space lattice, we take a point at the origin of coordinates and move it in the given direction until it passes through the first lattice point whose coordinates are small h small a, small k small b, small l small c. The indices of the direction are then small h, small k, small l, and it is customary to write it within square brackets, that is square bracket of HKL. This operation is equivalent to saying that the desired movement can be accomplished by moving along the x-axis at distance h times unit distance small a, along the y-axis at distance small k times the unit distance small b, and along the small z-axis at distance l times the unit distance small c. So, square brackets enclosing 3 indices specify direction indices. The normals to crystallographically equivalent planes are crystallographically equivalent directions. The complete set of crystallographically equivalent directions of which square bracket HKL are a member is denoted by enclosing the direction indices in angle brackets such as angle bracket HKL. In case of cubic crystals, as for an example, a direction represented by direction indices square bracket HKL is normal to a plane whose Miller indices are HKL with normal brackets. Some important crystallographic formulae. Interplanar spacing. The interplanar spacing small d between adjacent planes holding Miller indices HKL are given by using the following equations relevant to the crystal system to which they belong. The axial lengths of unit cell are represented by A, B and C, whereas their axial angles are represented by alpha, beta and gamma. For a triclinic system, the formula is 1 upon d square is equal to 1 upon v square within brackets W111 h square plus W22 k square plus W33 l square plus twice W12 hk plus twice 23 kl plus twice W31 hl. For a monoclinic system, 1 upon d square is equal to 1 upon sine square beta into h square upon a square plus k square sin square beta upon b square plus L square upon c square minus twice HL cos beta by AC. For an orthonormic system, 1 upon d square is equal to h square by a square plus k square by b square plus L square by c square. For a tetragonal system, 1 upon d square is equal to h square plus k square upon a square plus L square upon c square. For a cubic system, 1 upon d square is equal to h square plus k square plus L square upon a square. For the hexagonal system, the formula is 1 upon d square is equal to 4 by 3 into h square plus hk plus k square upon a square plus L square upon c square. For a trigonal system, 1 upon d square is equal to h square plus k square plus L square into sine square alpha plus twice hk plus kl plus hl into cos square alpha minus cos alpha upon a square into 1 minus 3 cos square alpha plus twice cos cube alpha. In this formula, v square is given by a square b square c square into 1 minus cos square alpha minus cos square beta minus cos square gamma plus twice cos alpha cos beta cos gamma, and W11 that we have used for triclinic system is equal to b square c square sin square alpha. W22 is equal to a square c square sin square beta. W33 is equal to a square b square sin square gamma. W12 is equal to abc square into cos alpha cos beta minus cos gamma. W23 is equal to a square bc into cos beta cos gamma minus cos alpha. W31 is equal to ab square c into cos gamma cos alpha minus cos beta. Now we come to the formula for interplanar angles for different systems. Let us consider planes with Miller indices h1, k1, l1 with interplanar spacing d1 and the plane with mirror indices h2, k2, l2 with interplanar spacing d2. If these two sets of planes make an angle theta with each other, its value can be found by application of the following formulae. For a triclinic system, the formula is theta equal to cos inverse a upon b subscript h1 k1 l1 minus b subscript h2 k2 l2, where capital A is given by h1 h2 b square c square sin square alpha plus k1 k2 a square c square sin square beta plus L1 L2 a square b square sin square gamma plus ab c square into cos alpha cos beta minus cos gamma into k1 h2 plus k1 k2 plus ab square c into cos gamma cos alpha minus cos beta into h1 l2 plus l1 h2 plus a square bc into cos beta cos gamma minus cos alpha into k1 l2 plus l1 k2, and b hkl is given by h square b square c square sin square alpha plus k square a square c square sin square beta plus L square a square b square sin square gamma plus twice hk c square into cos alpha cos beta minus cos gamma plus twice hlab square c into cos gamma cos alpha minus cos beta plus twice KLA square BC into cos beta cos gamma minus cos alpha raised to 1 by 2. For monoclinic system, theta is given by cos inverse h1 h2 by a square plus k1 k2 b square sin square beta plus L1 L2 by c square minus 1 upon AC into L1 H2 plus L2 H1 cos beta. divided by h1 square by a square plus k1 square by b square sine square beta plus L1 c square minus twice h1 L1 ac cos beta into h2 square by a square plus k2 square by b square sine square beta plus L2 square c square into twice h2 L2 by ac cos beta raised to 1 by 2. For an orthorhombic system, theta is given by cos inverse h1 h2 by a square k1 k2 by b square plus L1 L2 by c square divided by h1 by a whole square plus k1 b by whole square plus L1 by c whole square into h2 by a square plus k2 by square plus L2 by c square raised to 1 by 2. For tetragonal system, theta is given by cos inverse L by a square into h1 h2 plus k1 k2 plus L by c square into L1 L2 divided by 1 upon a square h1 square plus k1 square plus L1 square by c square into L by a square h2 square plus k2 square plus L2 square by c square raised to 1 by 2. For cubic system, theta is given by cos inverse h1 h2 plus k1 k2 plus L1 L2 upon h1 square plus k1 square plus L1 square into h2 square plus k2 square plus L2 square raised to 1 by 2. For hexagonal system, theta is given by cos inverse h1 h2 k1 k2 plus k1 k2 plus L1 L2 plus 1 upon 2 into h1 k2 plus k1 h2 plus 3 by 4 a square by c square L1 L2 upon h1 square plus k1 square plus h1 k1 plus 3 by 4 a square c square L1 square into h square plus k square plus h2 k2 plus 3 by 4 into a square by c square L2 square raised to 1 by 2. For trigonal rhombohedral system, in this case, the trigonal rhombohedral indices are first transformed to hexagonal indices using the transformation matrix, and then the formula used for hexagonal system as given above can be applied. Matrix HT, KT, LT is equal to matrix 2 by 3, 1 by 3, 1 by 3, minus 1 by 3, 1 by 3, 1 by 3, minus 1 by 3, minus 2 by 3, 1 by 3 into matrix HH, KH, LH. Then we come to the formula for volume of a unit cell. Triclinic system, volume given by V equal to ABC into 1 minus cos square alpha minus cos square beta minus cos square gamma plus twice cos alpha cos beta cos gamma raised to 1 by 2. For monoclinic system, volume is given by ABC sine beta. For orthorhombic system, V is equal to ABC. For tetragonal system, V is equal to A square C. For cubic system, V is equal to A cube. For hexagonal system, V is equal to under root 3 by 2 A square C, which comes out to be equal to 0.866 A square C. For trigonal system, or what we call as rhombohedral system, V is equal to A3 into 1 minus 3 cos square alpha plus twice cos cube alpha raised to 1 by 2. So students, let us summarize what we have learned in this module. We had the concept of Miller indices as has been given here. The procedure of how to assign Miller indices to a particular plane is explained. Also, the procedure for assignment of Miller indices enabling to describe orientation of any plane is also explained. Example of a crystal with planes of Miller indices 001, 010, 001 bar, 100 and 01 bar 0 is illustrated. Procedure for assignment of crystallographic direction has also been explained. Important crystallographic formulae regarding interplanar spacing, interplanar angles, and volume of unit cell for different crystal systems are given. Thank you.